Okay, we're back. So now we're going to jump into the etiology of adiposopathy. And particularly, we're going to focus on obesity-induced insulin resistance. So a couple of quick things first. First of all, if we look at data, and this is old data, and I should go back and get new data, and I will at some point, but not yet. When we look at the comparison between the 1976 to 1980 NHANES data, so NHANES, you should remember, but it's a large national study in the United States that's nationally representative. And what I mean by that is that they randomly sample the US population. They do it based on zip codes, and then inside those zip codes, they randomly sample households, and then they do weight their data as well to match up with the US Census data. So what that means is if they only have, for whatever reason, 5 Hispanics in this study, right? They will weight their data proportionate to how many Hispanics are in the US population. So it's a strong study design. It helps us believe that the results are representative of individuals in the US more so. So if we take NHANES data from 1976, the average BMI was 25. So the mean was 25, and you can see there's a pretty normal distribution around it. We would expect a normal distribution, by the way. If the larger your sample size, the more likely you are to get a normal distribution. So pretty normal distribution with the mean being 25. What we see now is that if you look at the 2005, 2006 data, right, now the average BMI is, in the study when they did the analysis, it was 30. Here, right, when we look at this red line, it might appear like it's a little lower than that. We might be closer to like 27, 28 or so. But what you can very clearly see is the area under the curve. So if we look at 30, right, that's the cutoff for obesity. If we look at 30, you can see that in the blue line, the area under the curve is right here, right? Okay, so that represents the number of people in the population who are considered obese. Now, when we consider the red curve, right, there's this area in between the two lines. That is the extra proportion of the population that is now considered obese. So we have a pretty significant difference already there, and that difference has grown in the last 20 years. Okay. We have seen it level out, just for the record, in the last probably 5 to 10. So really most of that growth would have happened between 2005 and 2015. Okay. In talking about insulin, it's helpful to have some understanding of what's going on. So insulin is produced in the pancreas in response to calorie intake. So generally in response to glucose, but it can be in response to triglycerides in the blood as well. Insulin's produced in the pancreas here, so that's that bottom left corner that you see, in beta cells. So there's light blue. There are also alpha cells in the darker blue. That's where glucagon is produced. So slightly different actions, and we won't get into glucagon now, but that's where it's coming from. Okay. And then we see this picture in the upper left-hand corner. Okay. So you have these insulin receptors, right? So glucose is in the bloodstream. So out here's the bloodstream. Glucose comes in, or glucose is in the bloodstream rather, and then insulin in the second picture you see is attaching to the insulin receptor, which then allows this guy here, it's called the GLUT4 receptor, to come up toward the surface, and then that allows glucose to enter the cell. So GLUT4 receptors are something that you'll hear about quite a bit. There are other GLUT receptors, but this is the one that's really important for insulin. Okay. Okay, and then this bottom right picture, it's hard to see, but this is just a picture of what insulin resistance looks like. So you can see the amount of insulin in the blood and at what time point after someone has eaten a meal. So this is what we would consider a healthy person in this left graph. So we see that insulin peaks about 60 minutes after, then it starts to go down, and then we've dropped to about normal levels about 3 hours after a meal. Okay. In somebody who has insulin resistance, insulin isn't actually peaking until the 120-minute point, and it barely drops at the 180 point. So it might not be dropping to normal levels for a long time actually after. So basically we have a lot more insulin sitting in the blood for a lot longer period of time, which also may indicate, right, that we have more glucose and fatty acids sitting in the blood for a longer period of time. We'll get into why that's an issue in 2 weeks. But really briefly, right, it would contribute to my risk of injury to my blood vessels, right? And then that could lead to atherosclerosis, which could be a contributing factor to cardiovascular disease. But I wanted to give you some terminology and some background to support what we're going into. So again, coming back to this figure, we will do this a lot this semester, right? I just want to focus on where we're talking. So really today, it's mostly right here. So we're talking about sort of the connection between obesity and type 2 diabetes. And we're doing that through different mechanisms. So we'll start with a positive energy balance, and then we'll talk about adiposopathy and dyslipidemia and how those contribute to insulin resistance. And you'll see a tiny little blip about atherosclerosis in here as well. So just a heads up of where we're at. Okay, so the etiology of obesity-induced insulin resistance. So first, we have to deal with an energy balance. So we have a positive energy balance. And I know this is a small figure. I'll talk you through it. When we're talking about energy balance, right, we're talking about the difference between energy intake and energy expenditure. Okay, so energy intake is just the fats, the protein, and the carbohydrate that you ingest. Some people would also include alcohol and water on this. Water has no calories. Alcohol is associated with about 7 grams or 7 calories per gram. So alcohol really probably should be on here, but most of the time people might include that with like carbohydrate intake. Okay, so in any case, and then that on the other side of the scale, we have your resting metabolic rate. So that's if I did nothing, my body still needs calories to function. I can't just not eat, right? So my brain is still active, my liver is still active, my kidneys are still active, and I need calories for that. So that's my resting metabolic rate. TEF stands for your the thermic effect of food. So that's usually about 10% of your total energy expenditure is from the thermic effect of food. And all that means is that it takes my body some energy. If I give it a peach, let's say, I just had peaches and cream, it was delicious. If I give my body a peach, right, that has some carbohydrate associated with it. I also gave it some fat in the cream that came with it. And I gave it a little bit of sugar because I put a little sugar on top, okay? So I just gave my body those calories, but my body can't just take that peach and convert it into body tissue. It can't, that's not possible, right? Otherwise we would see like a small peach growing out of me right here, right? It has to break down that food, and that requires energy. Okay, so that's the thermic effect of food. Then we have SPA is how it's listed here. So that's spontaneous physical activity. More often in the research literature now, you'll see it listed as non-exercise activity thermogenesis. So NEAT. So people will call it NEAT, your NEAT. All that means is any activity that is not intentionally exercise, but is still movement. So when we're looking at domains of physical activity, right, that would include any domestic tasks, that would include any transportation, that would include gesturing with my hands, right? So any type of movement that's not exercise, even potentially something like gardening might be considered neat. And then lastly, we have exercise, right? And exercise, depending on the individual, is going to take up a different proportion of their calories. But generally speaking, with weight gain, right, we might see slightly, our RMR is, the combined energy expenditure is less than the combined energy intake, right? Whereas with weight loss, right, we see that the energy intake is lower than the energy expenditure, right? And in this figure, right, we can see exercise got a little bit bigger. SPA didn't really change much. Thermic effect of food didn't change much. RMR maybe increased a tiny bit, but mainly it's showing it from exercise here and from a decrease in energy intake. Okay, and then weight maintenance would mean they're balanced. So I would like to invite you to take a couple of minutes and think about all of the ways that we might be changing someone's energy intake or changing someone's energy expenditure. Just try to think about a real person. How does this look for Jason? Or how does this look for Michelle, my mom, or Stan, my dad, right? Like think about somebody that you know and think about, okay, what's changing here? Okay. Okay, so when we do have positive energy balance chronically, that leads to AT is adipose tissue. So adipose tissue hypertrophy and hyperplasia. So that's demonstrated in this upper left-hand corner. So first we have, right, a baseline level of adipose tissue. In some cases, we see that adipose tissue simply get bigger. And in other cases, we see that adipose tissue multiply essentially. So instead of bigger cells, we just have more cells. And that's largely genetically determined. Generally speaking, what we see happen in obesity is these larger adipose tissue cells. We also have different types of adipose tissue. So you have white versus brown, and that's demonstrated up here. So you can see that this brown has much fewer lipid droplets is what they're called. So sort of baby fat inside of a fat cell, essentially. But you can also see that there's these other organelles involved, particularly the mitochondria and the nucleus. Okay, so there's a lot more mitochondria in brown adipose tissue, meaning that it is much more metabolically active. So it's actually utilizing more calories, and it's mainly involved in thermogenesis, so in the production of heat. So if I'm cold, right, I might need more brown adipose tissue to kick in to help me not be so cold. Generally speaking, higher amounts of brown adipose tissue are associated with better health or healthier fat, and then higher amounts of white adipose tissue is generally less healthy for you. Okay, so I chronically have a positive energy balance. My fat cells are hypertrophying, which leads to increased lipolysis and FAs, fatty acids, or lipotoxicity. They're the same thing. So, but you'll see lipotoxicity in the literature, so I wanted to bring it up. All that means is, right, the fat cell is now large enough that it says, I can't get any larger. Therefore, it activates some enzymes to help get rid of some of its fat, essentially. Okay, so and this is part of what does that. So typically we see decreased LPL, so lipoprotein lipase, and increased HSL. Now, in a healthy individual, insulin usually leads to increased LPL and decreased HSL. So increased LPL would then cause the body to store more fat and to stop breaking down fat. In this case, we see decreased LPL and increased HSL activity. So now I'm actually breaking down fat tissue and I'm putting free fatty acids into the blood. Okay, that process is known as lipotoxicity, which then results in inflammatory molecules such as TNF-alpha and IL-6 to be released. We also see down here that there's generally insulin would cause decreased VLDLs. In this instance, it's actually causing increased VLDLs, okay? So healthy response, we would see decreased VLDL once we're at the point where adipose tissue is no longer healthy, so adiposopathy, right? Then I'm actually seeing increased VLDL production. Okay. Okay, so then if I experience that chronically, right? So I may have a bout of that, right? That's not an issue. But if I'm chronically experiencing lots of free fatty acids in the blood, as well as these inflammatory molecules, right, that can lead to ectopic fat storage and hypoxia. So hypoxia is sort of demonstrated in this upper left-hand picture. So when a fat cell gets so large, it's really difficult for the blood vessels to adequately give that cell adequate nutrients. Okay, because it's like, so say I have a or a fat molecule this large, it's hard for my blood vessel to actually get all the way around it and feed it properly, which means that parts of the fat cell actually are going to die because they don't get oxygen, right? And without oxygen, our cells are going to die. With that, that's what we would call hypoxia, right? And we'll talk about what that looks like next. But ectopic fat storage, so especially visceral fat storage, is one of the key markers of obesity. Now, obesity is just diagnosed with BMI at the moment, but it's generally, high BMI is generally associated with greater visceral fat or ectopic fat. Okay, and that's fat stores where we don't want them to be. So generally, we want fat to just lie right underneath our skin, and that's our subcutaneous fat, right? Visceral fat in places it shouldn't be are in places like the pancreas, the heart, skeletal muscle, and the liver. So we're going to focus mainly on the liver. And what happens in the liver is not crazy dissimilar from what happens in skeletal muscle tissue. So, but in the liver, we have this molecule. You can't see it in that little tiny arrow, but it's called ApoB that gets produced and then sort of triggers this process that creates larger VLDLs. So what the liver is trying to do is it's trying to offload this excess fat, right? So I have these free fatty acids in the blood and the liver is trying to be helpful. So then it takes up some of those, but then it realizes, oh, I've got too much fat. Therefore, it's packaging up some of that fat in these VLDL particles. And so the VLDL particles get much bigger. On average, you're looking at maybe like a 20% increase in size to dispose of liver lipids, right? And then it also results in smaller LDLs, and that's really atherosclerotic, meaning it's going to cause plaques to build up in my blood vessels, and we'll talk about that next week more. Additionally, less HDL, meaning I'm not pulling unhealthy fats out of the bloodstream as much, right? So HDLs are responsible for bringing cholesterol back to the liver for reprocessing. Okay, so I'm not doing that. And then lastly, gluconeogenesis and hyperglycemia. So I see much more glycated hemoglobin in this case, so HbA1c, because I've got so much excess glucose in my bloodstream. Okay, and those are all contributing factors to the development of type 2 diabetes. And again, we'll talk more about that next week. So with this ectopic fat storage and hypoxia, we see an immune response. So again, coming back to those inflammatory molecules, looking at things like TNF-alpha, IL-6, CRP is C-reactive protein, and then adiponectin, which actually has the reverse effect. So we see increases in TNF-alpha, IL-6, and CRP, but actually decreases in adiponectin, which would decrease my inflammatory response. So, and then we also see impaired mitochondrial function. And again, I think we'll talk about that maybe more in the second half of the semester, but I wanted to throw it up here because it is part of this process. The other thing that's on here is those saturated fats. So an increase in saturated fat intake is associated with this inflammation process, independent of excess adiposity. Okay, so that's partly why a lot of like dietitians, for example, will recommend that not a large portion of your diet come from saturated fats, because even if I had a healthy body weight, I'm sort of skipping this whole process and jumping right into an immune response and increased inflammation as a result of high saturated fat intake. And then also with this ectopic fat storage, we typically see leptin resistance. So we see higher amounts of leptin in the body, but it's not actually doing its job. So generally speaking, leptin will control hunger cues a little bit. So it would then decrease my hunger cues, and it would still release some TNF-alpha and some IL-6, but in these unhealthy levels of adiposopathy, we see that as significantly contributing to inflammation. So again, that immune response. Oh, I should mention one other thing. With this immune response, sorry, so you have some other molecules, and we'll talk more about these in atherosclerosis, but MCP1 and macrophages. Macrophages are sort of the genesis of everything. They start this process, and then we typically see more of these inflammatory molecules called cytokines and adipokines come out. MCP1 is more involved in directing the immune response. So we'll talk about that more with atherosclerosis, but I should have mentioned those just so that you have exposure to them. There are a lot more adipokines and cytokines. These are just some of the more common ones that you see in the literature associated with obesity, and especially obesity-induced insulin resistance. Okay, so then we develop insulin resistance, meaning my body's not going to respond appropriately to insulin. I may experience higher levels of blood glucose. I may experience higher levels of free fatty acids in the blood. And I certainly will experience high inflammation. There's some interesting argument, and if you pull up the PowerPoint, you'll see a couple of citations in my notes sheet. You can go read those if you're really interested in it. There's some argument about whether or not inflammation and insulin resistance are actually related, or if they're two separate things. And to me, the research seems to suggest that actually they are two separate events, which is why they get their own sort of categories here. In any case, it does seem that both are occurring simultaneously and contribute to the development of type 2 diabetes. Okay, what does physical activity do then? How does it get in the middle of this process? The physical activity decreases. It literally has the exact opposite effect on all four of these molecules. So where ectopic fat storage would lead to increased TNF alpha, increased IL-6, increased CRP, and decreased adiponectin, physical activity increases adiponectin and then decreases CRP, IL-6, and TNF alpha. Okay, so physical activity can help combat, at the very least, the inflammatory process. Okay, in talking about, and I should have probably included this in the beginning for context, but with exercise and appetite, what we typically see is that, context for the slide first. Exercise is represented by the solid line in this left picture. And then the dotted line represents active sedentary behavior. So it is helpful to can't speak. There is a difference between active sedentary behaviors and passive sedentary behaviors. So active sedentary behaviors are things like homework. It could be working on a computer, right? Doing some programming, doing some writing. My brain is pretty active. Passive sedentary behaviors would be like watching TV or potentially playing a video game, although some people might argue that one. Okay. So this was an active sedentary behavior. And what we see is that physical activity seems to protect normal adipose signaling, so normal leptin and ghrelin levels. So my body is responding appropriately, and sedentary behaviors seem to sort of blunt that response. So physical activity is, in this case, associated with stronger hunger cues, right? Which makes sense because we're utilizing calories. Therefore, my body says, oh, I should replenish those calories that I've utilized. But active people also become sated sooner. So they ate breakfast here, right? Then they exercise, right? Hunger goes up for the exercise group. But then when they actually ate, we see that the active group is becoming sated quicker. But when we look at absolute and relative levels, so in this right-hand side, right, when we look at absolute levels, right, the exercise group still ate more, significantly more. So that's what that asterisk means. They ate significantly more than the control group, but the REI, so the energy, the relative energy intake was also significantly different. I wish these were switched, but the energy expenditure in these groups was 492 calories. So during exercise, they expended, or not during exercise plus their RMR, et cetera, was 492 calories in the exercise group, and in the control group, it was 197. So if you just take that top row and subtract it from the bottom row, you should get this third row, which shows that actually there was overall a less of a caloric intake, a total caloric intake in the exercise group compared to the control group. I think I explained that really poorly. If we have questions, let's come back to it in class. Okay, a couple of things I want you to consider when you're reading the article. So first off is, at one point it talks about BMI groups, and it groups a high BMI category and a low BMI category. The high BMI category is 27 to 54 kilograms per meter squared. Okay, that is this as if I took someone who was 5 feet 4 inches and they weighed anywhere between 160 and 315 pounds. Okay, that is a massive range. I don't know anyone who would think that somebody who's 5'4" and 160 pounds has the same physiologic processes or is at the same point in that physiologic process as somebody who is 5'4" and weighs 315 pounds. Those are clearly really different things. The average weight, just for the record, and this is very rough data, but the average weight for a female in the United States is 5 foot, or the average height is 5'4", and the average weight is 170.8 pounds. So that just gives you some context. So the average female is overweight. Similarly, for males, the average height is 5'9", and the average weight is 199 pounds. So again, overweight, but not actually obese yet. But again, the range for someone who's 5'9" is anywhere between 185 pounds and 370 pounds. Okay, so it's just helpful to look at these. I'm not discounting their findings or their associations. That's the other side of a bad sort of consumption of research literature, right? We shouldn't discount people's findings because of their limitations. We just need to understand that there were limitations, okay? And that is one of them here. Particularly when we consider that clinically meaningful weight loss, so not significant, not statistically significant, but clinically significant, meaning we actually do see improvements in health, maybe decreases in mortality risk, happen at low levels of weight loss, so 5 to 12 pounds. So the fact that this study sort of groups people who have, I guess I didn't do the math, something like a 150-pound difference into the same category when we can see improvements in health with 5 to 12 pounds of weight loss seems incorrect to me. Okay. And we see that happening in a dose response fashion. So it's particularly with type 2 diabetes. So however much weight you lose, we see that level of improvement in your mortality risk is all that's suggesting. Okay. Oh, the article specifically talks about that level of decreased risk for type 2 diabetes or for even remission of type 2 diabetes. Okay. At one point, the article also says something about an unchanged fat-free mass or unchanged muscle mass. I just want to mention so that when you're reading articles, you start to think about this as well. Unchanged does not mean that things didn't shift. Generally speaking, with age, so I think in this case, it was a 3-year longitudinal study. With age, we see decreased fat-free mass, okay? That's a negative. It's associated with negative health outcomes, okay? So if I see it unchanged across time, that's actually a win, okay? So oftentimes we think, oh, well, then that exercise intervention did nothing because it's the same values. No, that means that the exercise intervention really helped to maintain lean muscle tissue or lean tissue, despite the fact that we'd typically see that drop off with age. Okay, so don't think that unchanged is some null finding or that nothing important happened. Sometimes null is really good. And then also when you're looking at the physical activity piece of the article, I want you to consider, what about FitVP? Did they address the frequency? Is it important? And they do address frequency at least at one point in this article. So pay attention to what that is. Do they address intensity? Do they address volume? Do they address time, right? Sometimes we get in the habit of saying, well, exercise is just good for you. And maybe it is, but it is still helpful for people to understand, okay, but what type of exercise should I do? How much should I do? How intense does it need to be? Do I need to progress it, or can I see the same benefit across time with this certain amount, right? So all questions that I want you to be thinking about when you read the article. Okay, time to jump into the article, and I will see you in class on Thursday.